Good morning, everyone. I would like to thank the organizers for giving me the opportunity to present my work here. I'm from the Federal Fluminense University in Niterói. The city of Niterói is across the Guanabara Bay from the city of Rio de Janeiro, which you should probably be more used to. And the summary of my talk, I will start with some important concepts and the motivation for the work. In the second session, I'll present the methodology which we developed in the past few years, and then present the results and the discussion, and finally the conclusions and the perspectives for future works. So the first important concept is the Mott insulators, which is the principal uh, object of this methodology. So the story about the Mott insulators is related to some metal oxides, which according to the usual band theory should present a metallic behavior because of the odd number of electrons in the last band. But experimentally, they were observed to be insulating materials. So the first scientist which theorized what would happen in those materials was Professor Neville Francis Mott, which idealized that in those materials the electronic correlations were so high that the conduction band would split into two, where the lower band would be completely filled and the upper band would be empty, and there was a gap between the two bands, and therefore the material would be an insulator, and those kinds of materials became known as Mott insulators. And the first one to propose a simple model to explain electronic correlations in materials was Hubbard. Of course, everyone is familiar with the Hubbard model. It has a kinetic energy term with the hopping terms. It has the electronic correlation denoted by U. In this work, I have also included a magnetic term, which will be useful later, as I will show you. In his first work, he was able to obtain the insulating phases predicted by Mott. However, in his first approach, any value of U greater than 0, you would have an insulating material, so he was not able to reproduce the metal insulating transition. And the first time which they were able to solve the one-dimensional Hubbard model exactly was a work by Lieb and Wu, and which they used the Bethe ansatz to obtain analytical expressions for the ground state's energy, which is here, the band gap, and there is also an interpolative results by another group for the double occupied state, which are in the right side. But the main result it came a few years later by the thermodynamic Bethe ansatz, which is the magnetic phase diagram, which is separated into 5 different phases, where phase number 1 is an empty system. Phases number 2 and number 4 are an occupation between 0 and half. Phases 3 and 5, the system is half filled. However, in phases 2 and 3, the system have only spin-up electrons, and in phases 4 and 5, you have both spin-up and spin-down electrons. And what is nice about this solution is that phase 5 is what represents a Mott insulator. And the motivations for a new methodology, the first one is the construction of a general method which can be used for general cases where there are no exact solutions, such as the one-dimensional Hubbard model outside the half-field case, and models in 2 and 3 dimensions to be able to obtain the Mott transition in a consistent way. And two other motivations, the other methods they use exactly diagonalization. They use the eigenvalues and eigenvectors, but do not calculate the atomic Green's functions, which I will show they are very important to study the different approach, the different processes inside the model. And also a third motivation is that we want to be able to develop a methodology that can be used for any parameter spaces of the model. such as the electron density, chemical potential, temperature, electron correlation, etc. Before entering the method itself, I'll show a little bit about the cumulant expansion for the Hubbard model, which was obtained by Walter Metzner. Starting for the Green's functions, the single particle dependent, temperature dependent Green's functions, he was able to perform a diagrammatic expansion in the limits of infinite dimensions, and he showed that the Green's functions were related to the cumulants by this kind of Dyson equation, which has an exact solution in this way. Or in terms of the self-energy, as is commonly used by the dynamical beam field theory, these cumulants can be written in terms of the frequency, the chemical potential, and the self-energy. And starting by these Green's functions, we were able to develop a methodology to obtain these cumulants, to obtain the Green's functions for the lattice in the Hubbard model. So the main idea of the method is to start from a chain of atoms that present correlation. For this work first in one dimension, and obtain the Hamiltonian for this chain, exactly diagonalize it, and from the eigenvalues and eigenvectors obtain the Green's functions in the lemma representation, which is under here. And from the Green's functions in the lemma representations, we can also separate this Green function in a matrix form, where the spin-up states is in the upper left corner, and the spin-down states are on the right lower corner. And the main approximation is made in here, where we use these Green functions as an approximation from these cumulants to be used on the expression which I showed on the past slide. And since I have separated the Green's functions for a small chain into a matrix, we can also do the same thing for the Green's functions for the lattice. I'll skip ahead because it's just a matrix algebra to obtain the partial Green's functions. And what is important is that from this partial Green's functions and the Fermi function, we can obtain the occupations of empty states, of up states, down states, and the occupation of doubly occupied states in the system. And by using this approach, we were able to recover the completeness for this problem, which is the sum of the partial occupation numbers is always recovered as the unity. And from the occupation numbers, we can also calculate the average electron density per site from the up states, down states, and the doubly occupied states. And also from the doubly occupied states, we can calculate the ground state energy of the model, which in general is calculated from this expression. The ground state energy from U equals to 0 is down here. And this integral can be made using the doubly occupied state number, which I showed in the previous slide. So first for the results for zero magnetic field, I will start by showing the residues for the Green's functions, which is the numerator for the expression of the Green's functions related to the cumulants. And as you can see, as the size of the chain increases, the number of these residues increases very rapidly, but their values also decreases very rapidly. So they are smaller and smaller as we increase the size of the chain. Here is an example of a density of states obtained from the method. We first use the constant dispersion relation because the properties we are going to benchmark are not related to the shape of the band. And we can see that for n equals to 7, there are several peaks. And we expect that as the size of the chain increases, it will go to a limit where it's more continuous. And to compare with the one-dimensional solution, we have also obtained the ground states energy, the doubly occupied states, and the gap on the density of states as a function of U. You can see that as the number of sites in the chain increases, the results always converge very nicely to the results for the one-dimensional Bethe ansatz. And here are the results for the occupation numbers. We can see the occupation numbers for the empty states in black, the up states in red, the down states in green, and doubly occupied states in blue, the completeness relations in magenta, and N is the average electron occupation in the chain. The occupation numbers for the empty states decreases as we increase the chemical potential. The up states and down states increase to the maximum value when the system is half filled, and then decreases as the number of doubly occupied states goes up. The completeness relation is always satisfied, equals to 1. And we can also see that the average number of electrons in the site increases up to 1 when half filled, and then goes up to 2 when the system is completely filled. But we can also see these steps which are associated to the change in the number of electrons in the ground state of the system. And this is very, very prominent when you have a small chain or very low temperatures. But we can see that as the temperature increases, these curves get much more or less step-like and very much more step-like, much less step-like. And now for the results for non-zero magnetic field, here I have 4 examples for the magnetic field 0.10 varying the number of sites, and we can see that depending on the number of sites, the behavior is different from each other, depending if the chain has an odd number of sites or even number of sites. But they all share the same general behavior. And now for a fixed number of sites, but increasing the magnetic field, we can see that for low magnetic field, the number of up states is greater than the number of down states. And as the magnetic field increases, the number of up states keeps increasing up to the point where there are only spin-up states in the system, and the down occupation numbers is 0. And from this occupation number graphs, we can also obtain the phase diagram to compare with the thermodynamic batch ansatz. Here I have the results for 5, 6, 7, and 8 sites. And we can see that as we increase the number of sites, the results get really close to the batch ansatz. We were able to recover the 5 phases which are obtained in the thermodynamic batch ansatz. But we were also able to see a small phase over here for low magnetic fields, which is the same phase as the number 6, but with a spin down orientation, even if we only consider a spin up magnetic field. So the overview of the method is that the results can be obtained in the straightforward manner. We don't need to perform any self-consistent or mean field procedures. The atomic cumulants calculated in the Matsubara frequencies do not present any problem of analytical continuation. The density of states is always positive. The completeness relation is always satisfied. There is a gap in the density of states for any finite value of u greater than 0. And so we were able to recover the behavior of the one-dimensional Hubbard model, which was expected. And the problem is that since we are using an exact diagonalization method, it relies on robust computation because the matrices are very big, and we also need a lot of memory to store all of these Green's functions. And to show a little bit what else we can do with the method, I brought you the results for the single impurity Anderson model, which is in its final stages. We were able to calculate the density of states using this method and compare with the NRG, which is the black curve. Here is a zone near the 0 energy, and we can see that for 10 sites, the results for the Kondo peak is really close to the NRG. However, we were also able to recover the lower Hubbard band, and the upper Hubbard band with the NRG is famously known for not recovering very well. And the extension for the two-dimensional Hubbard model is underway. And the only thing we need to change is the cumulants, that instead of solving a linear chain, we need to solve a two-dimensional system. And we need to change the dispersion relation for the dispersion relation of a real two-dimensional material. I would like to acknowledge my collaborators and the funding agencies, and thank you all for your attention.
Questions, please. Sorry, and in with this method, would it be easy to try to tackle multi-orbital problems?
Can you talk a little bit closer to the microphone?
Yes.